Oh, hi. Welcome to part P of chapter 7, Thermochemistry. In part P, I will cover section 7.5, measuring of change in internal energy for chemical reaction. This is constant volume calorimetry. In the section 7.6, enthalpy of reaction. This is enthalpy is just the heat of reaction. In a chemical reaction, some reaction absorb heat from the surrounding, some release heat to the surrounding, exothermic, endothermic. I define those two terms in part A. And in section 7.7, we will look at the constant pressure calorimetry and how to measure the enthalpy of reaction, delta heat enthalpy of reaction or heat of reaction. Without wasting much time, let's look at section 7.5, measuring change in internal energy. Remember, E stands for internal energy of the system, which is the sum of potential energy and kinetic energy of the system. Calorimetry is the study of heat, basically given off by a reaction using what we call calorimetry. Recall how we calculated the change in internal using the heat and work exchange of heat and work by the system with the surrounding. We can determine our change in the internal energy by measuring Q and W. Remember, we calculated, but in part, in this section, part P, we will see how to measure the heat release or absorb and the work done by the system. The change in internal energy of the system at constant volume is the same as the heat of the system. Remember, system is where we are interested in, we are focusing. In practice, we cannot observe the temperature changes of the individual chemicals involved in the reaction. So instead, we measure the temperature change in the surrounding. If you are taking the lab course this semester, you may have, or you will do towards the end of the semester, an experiment on calorimetry where you will determine the enthalpy of a solution when you dissolve a solid. It can dissolve by either releasing heat or absorbing heat, or enthalpy of formation of a complex, or enthalpy of neutralization of an acid by a base, and so forth. To get that, you only measure the change in temperature. I'll show you the coffee cup calorimeter in a moment. So remember, the heat released by the system is the same as the heat gained by the surrounding. The only thing we changes is the sign. What I want you to look at is the Q for the surrounding. Q for the system is the same as the both of them is the same as the heat of the calorimeter. And a calorimeter is simply a device used to measure the heat involved in a chemical reaction. This is something we looked at earlier on, how to calculate the work, change in volume. Remember, pressure has to be in atmospheres, change in volume, volume should be in liters. And the system can change either, can exchange heat, Q in this case, with the surrounding using this equation, or it can exchange the energy in form of work. And we looked at how to calculate work using this equation against the external pressure, right? Volume has to be in liters for this equation to change to joules, which is the unit for energy. So in constant volume calorimeter, we use what we call the pump calorimeter. And simply, this is the cross-section of a pump calorimeter. It is an isolated, we call it isolated system, where a combustible sample is placed in a sample compartment hooked up with an ignition wire. This ignition wire is to ignite the sample. It will burn. This is to start the temperature of water so that it will equilibrate. We can measure the amount of heat released by the sample by taking note of change in temperature. Remember, change in temperature is final minus initial. So we can record the initial temperature and final temperature after the ignition. This is called the pump calorimeter. It measures both the internal, it measures both, or rather it measures the internal energy of the system as opposed to coffee cup calorimeter, which we'll see later on. So let's go back to calorimetry. We see this. Please add on to the vocabulary you need to remember in this chapter. Calorimetry is used to measure the thermal energy exchange between the reaction and the surrounding. In this case, this is the system and this is the surrounding. We use calorimetry. It's a process by which you measure the change in energy. Home calorimeter has a constant volume because the volume is not changing here, and we measure change in internal energy. Coffee cup calorimeter, that is constant pressure, measures only the heat of reaction. We'll see that, maybe asked down the line, the difference between the pump calorimeter and the coffee cup calorimeter. So pump calorimeter measures the change in internal energy. And remember, change in internal energy is the sum of kinetic energy and potential energy. We will use the same thermodynamic term. I define the heat capacity of the calorimeter. You may be given that, and this is C, uppercase C, and subscript cal. This means heat capacity of calorimeter, and it's expressed in kilojoules per degree Celsius, not joules per gram per degree Celsius. We talked about specific heat, but remember this will be in kilojoules. So that if you are to calculate in joules, you have to convert using the appropriate conversion factor. So this is another illustration of, a different diagram for for pump calorimeter. It's an isolated system. To calculate the heat evolved, given off by the system in the pump calorimeter, we use this equation. Q, remember CA here, C and then the subgroup right here. This is the heat capacity of calorimeter, and delta T, this is change in volume, basically final minus initial. This is change in temperature, not volume. This is change in temperature. Sorry about that. This is change in temperature. T final minus T initial, temperature initial. So we have to take into account the change in temperature here. This will be the heat of reaction where QRXN, this is the heat of reaction. We can use this equation to determine the reaction current in a pump calorimeter. Release or absorbed. So delta in pump calorimeter, we measure change in internal energy in pump calorimetry. But in coffee cup calorimeter, which you will use in the lab or you may have used in the lab, we measure the heat of reaction. This is change in, you read this as change in enthalpy of maybe even subscript there, reaction, changing enthalpy of reaction. And this is only in measured in coffee cup calorimeter. This we can use constant pressure, not constant volume. Constant volume, we measure this change in internal energy for the system. So let's see how we can determine the change in enthalpy for the reaction. So here is a question. When 1.550 grams of liquid hexane, C6H14 should be subscript for that, undergoes combustion in pump calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find the change in internal energy for the reaction for in kilojoules per mole of hexane. Heat capacity of the pump calorimeter determined separately or separate from this experiment is 5.73 kilojoules per degree Celsius So remember how to calculate. Let me just minimize this so that you can have my whiteboard see how you calculate the enthalpy for reaction. All right. Recall Q for the system. All right. Q for the calorimeter is the heat. Calorimeter times change in temperature. All right. So this will be where C calorimeter, we are given that this is 5.73 kilojoules per degree Celsius, and change in temperature is given by the final, which is 38.13 minus the initial is 25.87 units here degrees Celsius. Yeah. So Q for calorimeter, therefore, Q for calorimeter is 5.73 kilojoules per degree Celsius times. If you find the change for that, this will be rather everything here. Let's say if I define the difference using my calculator, change that to, this will be 38.13 minus 25.87. I have 12. This is 12.26 degrees Celsius, and everything will be 70. Look at this, 70.2498. If I cancel that kilojoules, this is more than what we need for. This is more than what we need for insignificant figures, but we cannot round it up until the last and the very end. So this is the Q for the calorimeter. So Q for cal is equals to negative Q for the system. Means giving of that, which means if we know that, remember from this equation, change in internal energy for the reaction equals to the Q negative Q for the system per mole. So here is per mole of the reaction because of how much do we have here? We need to find the number of moles. How I end up with this is because of the change in internal energy. We are talking about per mole of hexane, per mole of hexane. So if I know the change in internal energy for the system, it's talking about per mole. I need to divide by the number of moles in 1.55 grams. This alone is not the answer. This alone is not the answer. This is the total change in internal energy, but it's not per mole. Be careful when say per mole, you need to divide by the number of moles or you have in a sample. Next time it may not be hexane, it can be anything else, but remember to change the number of moles so that you divide the change in internal energy. You see this is per mole of hexane in this case, hexane. So number of moles of hexane is given by 1.550 grams times using the molar mass of hexane. This is 18 or 86.1. Use the periodic table, grams of hexane. This is 1 mole of hexane. All right, this will be 0.01 799 moles. Delta E reaction is equals to negative Q for system per mole. This equals to negative 70.2498 kilojoules over number of moles is 0.01799 moles. Remember, this is the number of moles in 1.550 grams of liquid hexane because of what we are asked, what is the change per mole. If it's only what is the change in internal energy for the reaction, and then we just give it a 70, round off to the correct number of significant figures. Very significant figures, this will be negative 3.92 times 10 raised to 3 kilojoules per mole, And this is the correct answer. Please go back again, take note of, you have this is times 10 raised to 3 here. Okay. And this is the amount or change in internal energy for the reaction in kilojoules per mole of hexane, if it's something other compound, please use the periodic table. By now, you should be able to write the correct formulas for your compound. We learned about that earlier on. So practice with this problem number 77, 78 on page 308. It's just about the combustion and combustion of substances in pump calorimeter. And you'll be asked to calculate the change in internal energy for the reaction, which means you need to calculate the Q for the system. You divide by the number of moles. Remember, you used the heat capacity. This equation we learned earlier on, this right here. This is what you need to recall from the previous section, that is part A, heat capacity of the calorimeter. Why you are given there is shortcut in joules. Proceed from there, and then you'll get a change in internal energy for the reaction per mole of substance, per mole of a substance. That is a constant volume calorimetry. It is the pump calorimeter. If you want to draw the parallel between 7.5 and 7.6, 7.5 is on pump calorimetry. Make your own notes. I know it's a short section. Read, define what a calorimeter is, what calorimetry is, what is all about the pump calorimeter, how to calculate the change in internal energy for the system, all right? And then you'll see, you should be able to handle problems on pump calorimeter. Now, section 7.6 enthalpy is simply the heat of reaction. This H means enthalpy of reaction, enthalpy of reaction. And this means change in enthalpy of reaction, change in enthalpy of reaction. It is a state function. We defined that earlier on, but the question is, how do we calculate the enthalpy for reaction? It's the same as the Q for the reaction at constant pressure. Delta H for the reaction is the same as the Q at a constant pressure. This is constant pressure calorimetry. Means the pressure is constant, is open to the atmosphere. We use the coffee cup for this. So remember, this Q is the same as heat of the reaction, which we use mass times specific heat times change in temperature. Times change in temperature. Behind this is what I do have on my whiteboard. You should be able to calculate that. Unlike in internal change in internal energy, which we measure both kinetic and potential, there is a small difference between the two, and sometimes can be the same thing. Here is a conceptual question still on combustion of butane. All right, CH410. When 1 mole of, you can see that when 1 mole of butane burns or combusts at a constant pressure, it produces 2,658 kilojoules of heat. That's 1 mole, and that's 3.8. It has 3 kilojoules of work. So the system is doing work, and at the same time, it is releasing heat to the surrounding. What are the values of change in internal energy? Change in enthalpy of the reaction. This is just the heat release. And what is the change in enthalpy? Change in internal energy for the reaction. This is enthalpy for reaction, heat of reaction, and this is the change in internal energy. You need to understand that this is just heat of reaction. You should have it subscript there, whereas this is change in internal energy of the system. Okay. Now, for this, it produces, that means it releases, it's going to be negative 2658 kilojoules. And for change in internal energy, it's the sum of the two. So it's going to be 2658 plus 3, which is negative 266 kilojoules. So if you look at this and this right here, this is what the question is asking for. This is just the heat of reaction, which is right here. Negative because produces, that means it releases. You see what I was talking about earlier on, it can be positive or negative, and you'll be wondering which one is which. Remember, the second part is the change in internal energy, which is the sum. So we're going to find the sum of the two. That's why we have this. We have to go back to how to calculate the change in internal energy. It is Q plus the work done. Remember, Q, change in internal energy is Q plus W, and both of them, they are negative, negative. The system is doing what? System is doing work, so it's negative W. Heat is released. Remember, it is produced, so it's gonna be negative Q, negative W. We go back to the convention again. In case you were wondering, how did I figure it out that it is negative and this one is negative, negative plus negative. By the way, that's why I have negative that. This is negative right here. Why do we have negative? Because the system is doing work, so it's negative. Why am I having negative here? It is being produced. So sum of the two will keep being negative 2,661 kilojoules. The correct answer is C. The correct answer for this is C. Double check that again. Go back, read how to find the change in internal energy. This is not something new to you, exothermic endothermic reaction. I know you covered in Thermochemistry. I've gone over and over exothermic endothermic reaction. If I use the diagram I used earlier on, if this is the system, all right, system, minus Q, which means delta H is negative. Carrying up, and then carrying in here, it is plus W, which means delta H equals to positive. Sign convention for the system, and remember where Q is the same as just the H, or change in internal energy, change in heat of reaction or enthalpy. So positive for endothermic reaction. So I'm gonna have here, this is endothermic reaction, and here this is thermic reaction, endothermic exothermic reaction. So for exothermic, it is negative. It is negative, and this is positive. You know, when it's in this form, you may not really tag when you have the system where the reaction takes place before C plus this is the system, and whatever is outside is the surrounding exothermic. All right. Use the energy, the diagram given here. When it is greater than, it means endothermic positive, and endothermic reaction positive. Less than zero is negative. That means it is lost. Negative, positive. It is given off. It is absorbed from the surrounding. Here is a learning check. When a reaction occurs in a flask, you notice that the flask gets colder. What is the sign of change in the level of the reaction? In other words, if this is the flask here, all right, if this is, or you cannot see, yeah, you can see it from here. If this is the flask and I hold it like this, it's feeling cold, right? It's cold. Do you expect what will be the sign of change in and the level of reaction? If it is getting cold, it is positive. That means it's absorbing heat from your hand. That's why you feel it cold. It's just the same thing as when you hold an ice cube. An ice cube is considered as the system. And when you hold it, you'll feel cold because it's absorbing heat from your hand. Therefore, the temperature of the ice cube will go up above 0 degrees Celsius and it will start melting. So the sign is positive for this. Please wrap around your mind all these conceptual questions. Just gonna give you just to avoid having all mass paid problem in a quiz or exam. A good example also here on the sign of and the level of reaction or heat of reaction, or H in simple terms. A chemical reaction that gives off heat to the surrounding. That means it's releasing. So you got to know how you look at that. Maybe if just like if I had that, you can see what's going on. So it's giving off heat to the surrounding. So it's going away. I see this is going to be negative. You say to be exothermic and has a dash value. Is it negative or positive? I see it's negative and it is exothermic. Exothermic negative. Exothermic negative. The correct answer is B. No. Exothermic negative. The correct answer is D. Exothermic, giving away heat, and then it is negative. The value for that is negative. Be careful on how you look at the side kind of problems, because if I look here, exothermic is in C and D. You may use elimination method. Some people may just focus on the first term, forgetting the second term here, and it will throw you off. So this is, if you may draw it, so welcome to draw using the strike paper in an exam so that you don't case yourself with this. I'm a visual person, and when I look at this, it makes more sense. It's easier for me to come to a conclusion in problems such as the one we have on the PowerPoint slide. Common problem that is not problem, but scenario exothermic, endothermic, they using the ice or cold pack, which contain ammonium nitrate, exothermic, endothermic, giving away heat, absorbing away heat. So this is just a summary of the value of heat of reaction, endothermic, and for exothermic, just reproduce that until you commit to your memory. So endothermic reaction has a positive and absorb heat from the surrounding. Endothermic, you see positive Q, delta H is positive. Exothermic, giving away heat, negative Q, delta H is negative for that as well. Oh, well, for molecular fuel of exothermic reaction, this is used for an exothermic reaction, the surrounding temperature raises. That means we are releasing heat to the surrounding. The extra thermal energy comes from the conversion of some of the chemical potential energy in the reactant into kinetic. So the power breaking and new bonds are formed, old bonds are formed, and heat is produced for that. You can also look at the molecular fuel for endothermic. This is exothermic. For endothermic, it's the same thing. During the course of the reaction, existing bonds are broken and new ones are formed, but the product of the reaction has more chemical energy, has more chemical potential energy than the reaction. That's the key difference between endothermic and exothermic. To acquire extra energy, some of the thermal energy of the surrounding is converted into chemical potential energy stored in the product. It's going to explain why we have higher energy for the product. We define extensive, intensive property way back when we were looking at the physical properties, chemical properties, we say some properties are extensive. That means it depends on the amount of substance. For example, volume. I can have 10 ml of H2O, but if I have 5 gallons of water, I'll have larger volume. So volume is extensive. Area is an extensive. We talked about all these extensive. Now coming back to envelope of reaction, which is delta H, it is an extensive property as well. The more you have assembled, the more you will have larger value for envelope for reaction. For example, here is a thermochemical equation, right? We call this thermochemical equation. Thermochemical equation is of this type: A plus B going to C, but you see there's delta H for the reaction, or just delta H negative 58 kilojoules, like that. We call this thermochemical equation. This is a thermochemical equation. And how you read this thermochemical equation is, for every 1 mole of propane, this is a propane gas, that react with 5 moles of H2O, no, not H2O, but oxygen gas, to produce 3 moles of carbon dioxide and 4 moles of H2O. This is the amount of heat which will be released. If I double this, it will also double. If I reduce, it will reduce, because it's an extensive property. Know how you interpret that envelope for reaction. Let's see, from the extensive understanding the extensive property of endothelial reaction, what is the heat associated with the reaction of 6 moles of A? This is pretty straightforward. You just have to use the dimensional analysis that for 6 moles of A, using what we are on the thermochemical equation here, we call this thermochemical, 2 moles of A produce or release 51 kilojoules, 51.0 for 3 significant figure. Those these will cancel, that will cancel. A and A will cancel. 3, so this is 153 kilojoules. It's gonna be released. Remember, it's not positive. Because it is negative here, we just use the mole ratio. For every 2 moles of A, is how much it will be produced. That's how much it will be produced for that thermochemical equation. Thermochemical equation. All right, so we're gonna have that. negative because it's exothermic. This is what I was saying earlier on. You have to be well-rounded with your numbers. Look at these two here. If you don't know what you're doing, you may even bubble it out if it is multiple choice, or you may click the wrong answer instead of getting the correct one. Do the math first before you narrow it down to specific. Make sure you set your work correctly. But the correct answer is negative, not positive, because it is released. Now, suppose you are not given the moles, you are given the actual mass. How you interpret the thermochemical? Again, we call this thermochemical equation. And for every 2 moles of peroxide that decompose 2 moles of H2O and 1 mole of oxygen, this is the amount of it released. This is the decomposition of hydrogen peroxide. Suppose you are not given the equation here, you need to use the polyatomic ion, your understanding of naming of the compounds, write a balanced equation. So calculate the quantity of heat released when 5.00 grams of hydrogen peroxide decomposes to the constant pressure. So for this, you need to find how many moles of this is how you proceed with the solution. Convert the given grams of hydrogen peroxide to moles of hydrogen peroxide. Molar mass of hydrogen peroxide is 34.0147 grams of hydrogen peroxide, H2O2. And then from the thermochemical equation here, for every 2 moles of hydrogen peroxide decomposed, is how much it is released. So we generate the conversion factor from the thermochemical equation that for every 2 moles of hydrogen peroxide that's consumed or break down, this how much it is given off, negative 196 kilojoules. Look at what is happening with the unit reconciliation. Is that reconcile that, we remain with the answer in kilojoules times, so this is going to be 14.4 kilojoules. 14.4 kilojoules will be released when 5 grams of peroxide decomposes. So we are making use of the thermochemical equation. Be careful when you are given a water problem with no balanced equation, you need to balance out that. Look at problem number 59, 61, 63, 65, 67 on page 307, 308 on thermochemical equation and calculation of the quantity of heat released or absorbed, released or absorbed. So that is determination of the enthalpy of reaction. Let's see. Constant pressure calorimeter measuring the heat of reaction. In the pump calorimeter, you measure or calculate the delta E. Constant volume is the pump calorimeter, but constant pressure, you measure the enthalpy for reaction. Enthalpy for reaction take place in the open atmosphere. We talk about the Q here for the surrounding, or for the reaction is the same as negative Q for the solution. And here, Q for the solution is given by the mass of solution times the specific heat of solution times change in temperature. Change in temperature. So here, When you look at that, it's gonna be negative. Find that mass of the solution. And for most part, if you have, listen, if you have reagent A, reagent B, both of them, you are putting them together, the total mass, the combined mass here is the total mass used in the reaction, total mass used in the reaction. This is what we looked at. Mass, specific heat for the solution, mass of the solution. And remember what we said earlier of solution is given by the solute plus the solvent, whichever you have the combined mass for the two, if they have the same amount. You can get the change in temperature, final minus initial. So enthalpy for reaction is the same as the Q for the reaction. That is the heat of reaction is the same at constant pressure. And to get the enthalpy for reaction, change in enthalpy for reaction, you divide by the number of moles. You divide by the number of moles. This is the calorimetry, which is basically the heat flow. The instrument used to measure the heat flow is calorimeter, which is 2 coffee cups insulated to avoid the heat being lost, so that you determine the temperature for that using a calorimeter. Let's say you have the same reaction with exactly the same amount of reactant is conducted in a pump calorimeter, in a coffee cup calorimeter. In one of the calorimeters, Q for the reaction is negative 12.5 kilojoules, and the other one negative 11.8 kilojoules. Which value was obtained in the pump calorimeter? Assume the reactioners are positive. So when I look at this, the correct answer is A, because it measures the total energy, the total internal energy of the system. If this is too small, if you have it here, measuring the, this is a work example, measuring the change in enthalpy for reaction using coffee cup. This is what I was talking about, having total volume, total mass of the solution. When a student mixes 50 ml of 0 or 1.0 molar HCl with 50 ml of 1.0 NaOH coffee cup in a coffee cup calorimeter, the temperature of the resultant solution increases from 21.0 to 27.5. Calculate the enthalpy of reaction in kilojoules per mole of HCl, assuming the calorimeter loses only negligible amount of the heat. That the total volume of the solution is 100, and the density. The reason why you are given density is to find the mass of the solution. Specific heat for the solution is just the same for water. Now, 1 degree Celsius is the same as 1 Kelvin. So this unit here is just the same thing as that. This unit, you maintain it, or rather use degrees Celsius here so that you reconcile the units. So analyzing the solution, you need to write a balanced equation. We need to calculate the heat produced per 1 mole. First, find the mass of the solution, because 50 plus 50 gives you total. Using the conversion factor, we have the density, and we know mass of the solution. Change in temperature, so that when you plug here for the reaction, this is how much you get negative 27 point, negative 2.7 kilojoules. But it is per mole, so we need to know how many moles we have in here. All right, so we need to find out you divide by the number of moles. This is the number of moles of HCl we have in 50 ml, and moles times, molarity times volume in liters give us the number of moles. And then we divide that by the number of moles. This is the enthalpy for the reaction per mole, depending on how much we have. Let's see, learning check. Ammonia react with oxygen according to the following thermochemical equation. 4 moles of ammonia react with 1 mole of oxygen to produce 4 moles of nitrogen monoxide, 6 moles of H2O, giving off -9 or 6 kilojoules. Calculate the heat in kilojoules associated with the complete reaction of 155, all right, 155 grams of ammonia. So this is how you proceed with that solution. First, change 155 over NH3 using the molar mass of ammonia, 1 mole of NH. It's just to find the number of moles in 155 grams of ammonia, times now from the thermochemical equation for every 4 moles of NH3, -9 or 6 kilojoules is given off. I cancel that moles and moles. This is more than what we need for significant figure, so it's 20 kilojoules is given off. For 3 significant figures, gonna be 2. All right. So remember the thermochemical equation, you read it from the balanced equation. 1 mole of oxygen will produce this. 4 moles of that will produce. So depending on what how the equation is structured, maybe here it will change to oxygen. So we're just gonna focus on that, what is given in the problem. Here is another example on thermochemical. What mass of butane in gram is necessary to produce 1.5 times 10 raised to 3 kilojoules of heat? What mass of CO2? All right. For this, whenever we are given 1.5 times 10 raised to 3 kilojoules using the thermochemical equation right here. This is how much is given. 266. This is 66. No, 58 is 58. So about that, this is 58658 kilojoules is produced butane. We are looking at the butane for every 1 mole of C for 4H10, this is 1 mole. What I'm doing here is from the balanced equation, 1 mole of butane releases this amount. So here, so that the units and units will go away, we remain with moles of butane. And then using the molar mass of butane, molar mass here of butane is 1 mole of C4H10. All right, H10 weighs 58. This is the molar mass, 58.17 grams of C4 H10 like that. H10 like that. So here is the cancellation for that. All right, gonna cancel out that. This will give you 33. Please check that 33 grams of C4 H10. You can take that as using thermochemical equation to predict how much will be produced. This is part A of the question, that what mass of butane in grams. I just have to reset that. This is from the thermochemical equation for every 1 mole of butane. This is how much it is given off. And then this is from the molar mass. We learned earlier on of the molar mass a while back. Use the periodic table. All right, if not given. Now, second part of the question is what mass of CO2 gas is produced on this? What mass? So again, in B here, solution given by 1.5, what is 5? 1.15, yeah, 1.15 times 10 raised to 3 kilojoules times, look, what we are given, 2650 what? 2658 kilojoules. For every 4 moles of CO2. Remember, we are looking at the moles of CO2 produced. Using the molar mass, this is from thermochemical equation, And then molar mass of CO2, this is 44.01 grams of CO2. Cancel that and we have that. So in total, this will be 99 grams of CO2. 99 grams of CO2. This right here is molar mass of CO2. It's used the periodic table. It's using the prior knowledge, okay, to answer the question, So that's how to use the thermochemical equation. Now, let's see, moving forward, precipitation reaction. The addition of hydrochloric acid to silver nitrate solution precipitates silver chloride according to the following reaction. All right, mole ratio is 1:1 to 1:1. When 50 ml of 0.100 grams of nitrate is combined with 50 grams of 0.1 grams of ACl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21. Calculate the H for the reaction, enthalpy for reaction is written. Use 1.00 grams per ml as the density for the solution, and the heat capacity is 4.184 as the specific heat. But the heat capacity, specific heat should be CS. So we are calculating the enthalpy for reaction. Remember, all right, well, Q for the reaction is mass times specific heat times change in temperature, where change in temperature is T final minus T initial. Final 24.21 minus 23.40, which is equals to, what is the change in temperature here? It is 24.21 minus 23.40, which is 0.81 degrees Celsius. We need change in temperature. Since we were given here the density of the solution, we are combining 50 ml and 60 ml. So if you want to find mass of solution, mass of solution is given by the volume as a conversion factor times 1 ml is the same as 1 gram. From here, use 1 ml per gram, so that ml and ml, this will be 100 grams of solution. 100 grams of solution, and we have the specific. Therefore, Q for the reaction is 100 grams times 4.184 joules per mole, no, per gram times degrees Celsius times 0.81, was it 0.8? Yeah, 0.81 degrees Celsius. So that this will cancel, that will cancel, this will cancel, that will cancel, and we'll remain with joules. We'll remain with joules. This will gonna be 338.9 joules. But per mole. Doesn't really matter if which one we use. Let's use silver nitrate. Number of moles, this is what we learned earlier of silver nitrate, AgNO3 is given by the molarity times volume in liters. It is 0.100 times 0.050. 0.005 liters. So I know the not liters but moles. It's going to be moles of silver nitrate like that. So if we want now, we're just going to plug that 338.9 moles. This is close to 60. This is for three significant figures. 67.7 kilo. So here is the key that for the enthalpy for reaction, it is the negative Q for the reaction, which you have to determine from mass times specific heat times the change in temperature final minus initial. You'll be given this. You maybe have to use the density equation to do that. How I did for that. And finally, you divide by the number of moles. Number of moles. So there we have the heat of reaction as written. You divide by the number of moles of silver nitrate, AgNO3. Look at problem number 79 on page 308. It's good practice on the calculation for enthalpy for reaction. This is the constant pressure calorimeter. Constant pressure calorimeter. Q for the reaction is the negative Q for the moles of silver nitrate. You'll see you'll use the same calculation in experiment number 10, calorimeter for experiment number 10. You are taking the course at UNF currently. This concept is on experiment number 10, calorimetry. This marks the end of part B.